Okay, the reviewer has the floor. Please start the time. The opponent has the floor.
Hello, my name is Jay Wong, and I'm here to propose the position for the problem rocking ball. The problem is as following. Fill a bottle with some liquid, place it on a horizontal surface, and give it a push. The bottle may first move forward and then oscillate before it comes to rest. Investigate the bottle's motion. I want to introduce the keyword here. The keyword push, move forward, oscillate before it comes to rest. Push, move forward, oscillate because it comes to rest. So the reporter has several strong points and weak points. And to start with the strong points. First, they did a good quantitative approach to investigate the phenomenon, and well explained that it's not a simple harmonic oscillation and made a complex equations. Now, they clearly explained and interpreted their data and error sources. Finally, they were polite and professional in presenting. However, they had some crucial weak points. First of all, they lack experimental control, because as they used a flat slope, it might make the rocking bottle bounce from the floor. And also, it had imprecise data with high variation. And with several, only 3 points to get the tendency. And also, they didn't focus what the problem really wanted, the pushing motion. And also, and I want to again emphasize that the inclined rail could be a problem. So I want to make a discussion today. These are the points for discussion. First of all, I want to talk about the validity of rigid body assumption in the theory, and then I'll talk about the mechanics of oscillating motion, and more about the restoring forces, and also the mechanics of damping effects, what really causes this damping effect, and also then I want to talk about the experiment setup, about the inclined rhythm. Next, I want to talk about the stopping oscillating motion, because they only consider the motion when it is still rolling. Since the problem is asking for the stopping motion, stopping oscillating motion, I believe that they have to talk about this. And then also there are several more discussion points. At first, I want to start with the validity of rigid body assumption in the theory. I thought that you first assume that it's a rigid body. You can assume that rigid body. However, if you get in the model that you got the friction force is actually the flow of the very thin portion is flowing. I think that's not a rigid body. What do you think?
So your argument is that due to the very thin layer near the internal side of the bottle.
Yes. Moreover, I want to talk that is the water, is the glycerin, is really like attached. It has the same angular velocity of the bottle. Yes.
Yeah. So your question about angular velocity. Imagine a situation when you have a bottle connected with a string, and you put a bottle with some water, and you give it an oscillating motion. Even though there can be some turbulent flow and vortex inside the water, the overall angular velocity of every point of the liquid will be almost consistent, which will prove the rigid body assumption.
Okay. But you had a different two model for get the friction. So is that just an assumption?
Yes. So the friction. First, I thought I might use the friction.
Yes, I know about that. Why you made the viscosity term? So I want to ask, isn't it different from your previous model? I know that your previous model is okay. Yeah. However, I think getting of two equation is different. Your model are a little different. And is it okay?
So are you talking about the simple harmonic model? I mean for the early stage of the stress. So the simple harmonic motion was actually intuitive model. Okay. I assume that the motion of the liquid.
Now I want to ask about the restoring forces that really actually make this kind of rocking ball. So what is the most important thing that makes this kind of rocking motion? What is the most important thing that you think that makes the rocking motion?
So I can go the possible forces acting on the both bottle and the liquid inside. Okay. So for the restoring force, there is the normal force and gravitational force and frictional force. Yet the most dominant force will be the normal force and gravitational force. And some of these two forces will always drag to the center line of the bottle, which will result in similar way to the physical pendulum. And when the liquid is tilted to the right side, the sum of these two forces will direct to the left side, and while the liquid is tilted to the left side, the sum of these two forces will direct to the right side.
Okay, so you are talking that some of the normal force and the gravity force is most important.
Yeah, that's the most dominant factor, and the frictional force is what actually damps the
okay, I got it. Then I want to talk more about that frictional force. You measured the damping effect by just only getting 2 points in your graph. Can you see your graph with the graph that you showed the damping effect? So you only get the 2 of the damping factor. And is it really constant? Is the damping factor really constant in such a motion? Because I believe that as it decreases the speed, the rocking ball decreases the speed and final stop. As it decreases, I think the damping factor could change. And I'm not sure that this kind of measurement is precise for getting a damping factor.
So actually for a function highly mathematical theoretical model, the damping factor might show as a function of the function in which there is E as a low. Yeah.
Okay.
In this rocking bottle phenomenon, I found out that as the phenomenon goes on at time, it becomes highly chaotic and hard to predict. So I only took care of the first and second.
I got your interpretation. However, so I'm talking about that. Is it really that damping factor by just 2 points is sufficient? I think you can get more points. After that, 4 or 5 more points, and then I think that will make more precise measurement.
So actually, I can get more damping factors, and maybe I can make a function out of it. It's really a good point. But what I found through observing this phenomenon is as oscillation repeats, the motion of the bottle actually gets highly chaotic, and the standard deviation when there's about 2 seconds after starting the oscillation.
Okay, I got it.
Results vary quite.
So where did you get the viscosity? Did you measure the viscosity of the glycerin, or did you refer? Where did you measure it?
So about the viscosity term, actually the viscosity is not the main topic of this research. So I studied a paper, formula for viscosity of glycerin water mixture, and I compared the ratio of the glycerin and viscosity at 18 degrees.
Okay, so I want to ask, what was your temperature, room temperature?
It was almost about 18 degrees Celsius.
Okay, thank you. And I want to focus on your experimental setup. Can I see your experimental setup again? Okay. So you said that you use an adjustable slant like that, and then see after the rocking bottle's motion. However, I think that if the bottle rolls down and hits the bottom, I think it will bounce off. And it's hard to control the rocking bottle's motion, isn't it?
Yeah, it's a really good question, and that was the exact problem I went through my observation. And as I take the motion of the bottle at this point, it actually bounces a lot when there is no material here. So I actually added some kind of a soft material.
Soft material to get rid of the bounce.
Get rid of the bounce. And still, when the degree of the adjustable slant was over 45 degrees, the bumping action actually occurred. So I controlled the degree to be less than 30 degrees, which showed no bumping action.
Okay. You said that you use a soft thing to get rid of the bouncing effect, and I think that can make making the bottle's motion slow, and that is a deceleration. And I think that could cause another force acting on your initial state of your rocking bottle.
So actually, interpreting the motion of the bottle when it is accelerating along the slip and as it reaches the floor is kind of another topic we can talk about. But in this research, I measure here. So you can see the tilted surface. The tilted surface is the major factor that causes the oscillatory motion. And if I set the initial angle between the tilted surface and horizontal surface, I can get the initial condition for my modeling and for the experiment.
Okay, thank you. Next, then I also talk about. Yes, I first want to ask, what is the most important parameters for this rocking bottle's motion?
So, with the flow chart, you can see I selected 3 parameters: the volume of the liquid, the radius of the bottle, the viscosity of the liquid. And
okay.
I believe that the viscosity of the volume of the liquid is the most important factor because it decides whether the rigid body model actually holds or not.
And you said that over 50% volume of that bottle, you said it's not a rigid body. And then what actual movement of the water inside, the fluid inside happens? I am very curious about it.
So, in this picture I show two situations where the volume ratio is low and volume ratio is high. So what you can see here, when the volume ratio is low, the angular velocity of the is almost consistent. However, when the volume ratio is very high, the rigid body assumption says that the angular velocity must be consistent in all parts of the liquid. However, what the actual phenomenon happening here is that the direction of the velocity is actually in reverse at the upper part of the liquid.
Okay, I got it. Thank you for your answering. And lastly, I want to question that I interpreted, or many of people can interpret this problem about the oscillating before it comes to rest, and the oscillating, the resting position. Before the resting position, I believe that there is an oscillating motion while not rolling. Not rolling, it has an oscillation motion. And why did you consider that motion?
Yeah, I actually considered the motion, and further improvement of my modeling might predict all along the fluid phenomenon.
Okay, so you are lacking the problem solving.
However, if you saw an oscillator motion just before the bottle stops, there might be problem with your horizontal surface setting because the oscillating motion just before the stopping actually happens when there is a little bit of flat in your setting.
Okay, thank you very much. Thank you for the discussion. Now the opponent, you have 1 minute to summarize.
So, first of all, I want to thank to the reporter for additional information. However, there are some still crucial weak points remaining. First, I think that their experimental setup it's not well controlled. And also, their interpretation of the problem was lacking because they only considered the rocking motion while it's rolling. However, there could be some more interpretation about the problem of oscillating motion before it stops. And also, I want to question about the preciseness of their experimental data, and getting the damping coefficient might be weak for getting only 2 peaks to get just 0.2 peaks. So this is the end of my opponent, and thank you for listening. Thank you very much.
Okay, now reviewer, please feel free to ask questions to the reporter and the opponent.
Thank you, the reporter and opponent, for a good physics fight. First, I'd like to ask a question to the reporter. You kept comparing the motion of the rocking motion as a simple harmonic motion. So I want to ask you, would the period of the rocking be different in the simple harmonic motion and the rocking bottle, which also has a translational motion?
So about that question, simple harmonic motion was my first intuitive assumption, and so in this graph, you can actually see there's a double peak shape at the maximum and minimum velocity, which means that the motion of the rocking bottle is not actually simple harmonic motion.
Could you just compare the case of the simple harmonic motion and the rocking bottle in terms of the period of oscillation?
In terms of the period of oscillation, the simple harmonic, when you assume that the pendulum is actually simple harmonic motion, you assume that the angle of the motion is below like 50 degrees. And in the rocking bottle, the degree of the initial degree of about 35 degrees. which can differ in period. And yet, as you can see in the pendulum, when the length of the pendulum increased, the period also increased. And the same tendency was shown in the rocking bottle.
Okay, thank you. And I noticed that you fixed the water surface as linear, is that correct?
Yeah.
But in the video that you showed us, the rocking bottle water surface was more like a sine function. Is there a reason why you set the surface of the water as linear?
So, for that question, so I noticed that the surface of the rocking bottle is not actually linear. But however, using this Java code, I could acquire the sum of coordinates of all the area highlighted by blue, and I could get the average value, which showed that this red dot here is the theoretical value of the center of the map, while the white dot is the experimental value acquired by this Java programming. So we can see that the center of the mass is actually almost in consistency. So this proves that the deformation of the 3D surface can be.
And I want to ask both reporter and opponent. You mentioned shear stress, and in calculating shear stress, do you think the viscosity of the fluid should be considered as dynamic viscosity or kinematic viscosity?
The equation I showed you is the dynamic viscosity.
The opponents, should it be dynamic or kinematic?
I think same with the reporter. Thank you very much.
Thank you for answering my questions.
Okay, reviewer, please take a couple of minutes to prepare.